we have arrived at my favorite part of chemistry, which is definitions. The reason I studied chemistry is because I like to memorize definitions. So let's do that together. Alright, so these are definitions for acids and bases. Let's just throw up a couple of acids and bases that we know. We know that hydrochloric acid is an acid. We know that sodium hydroxide is a base. We also know that ammonia, NH3, is a base, and then a weak base, and then acetic acid is another acid. So those are 4 examples. Let's take a look at these 3 definitions and see how they fit in, right? So the most simplest definition is the Arrhenius definition. It basically says anything that when dissolved in water produces hydronium ions is an acid, and anything that produces hydroxide ions is a base. So the hydrochloric acid is pretty obvious because hydrochloric acid will split apart into hydronium ions, or hydrogen or protons. They'll split apart into H+, which will of course attach to a water molecule to produce this hydronium ion. So definitely an acid. Same with lye, or sodium hydroxide, which produces hydroxide ions. So that's even more obvious. It doesn't have to react with water to furnish OH. The NH3 is more problematic because we can't really see. It does ultimately produce hydroxide ions, and acetic acid is not a big deal. One of these hydrogens comes off, and that's another thing that you might have struggle with or have to take a look at. Right? If you draw out the structure of acetic acid, and we looked at this already, there are several hydrogens here, right? So which hydrogens are acidic and which ones are not, and so that's something we might want to look at. It's only this hydrogen, because of this carboxylic acid part, that will come off slightly and then produce hydronium ions. But none of these are acidic, so they stay put. Now in your case, as you study for general chemistry too, it'll always be pretty straightforward. But anyway, so a broader definition is the Bronsted-Lowry, and we'll mainly go with it. That's the main definition I would recommend you're familiar with. It basically says acids are substances that when dissolved in water donate protons, and bases are substances that accept protons. So now all of a sudden we can take this NH3 molecule, ammonia, and say, well, it is a proton acceptor, because it can react with the proton it accepts that to form the ammonium ion, NH4. So that's definitely a base by that definition. You can maybe make an argument that if you take NH3 and you dissolve it in water, and this is in equilibrium because ammonia is weak, you are going to accept the proton here by that definition from water, which produces the ammonium ion. But what is left over then is the hydroxide ion, which up here by the Arrhenius definition, that's it. Bases are substances that when dissolved in water produce hydroxide ions. So you can actually make a weak argument, but it's still better to have the Bronsted-Lowry definition. Now the Lewis definition is actually the broadest and the best, but it's a little bit beyond the scope of this course. But it does include things like metals, aluminum, and this is something that you might want to remember. But aluminum is actually an acid, and it's a Lewis acid. So metals that are highly charged, and it's usually transition metals, never the alkaline earth or the alkaline metals are Lewis acids, and so they have to have empty orbitals to accept a lone pair of electrons, right? So aluminum has plenty of orbitals, and so it can accept electron density even from things like water. So water will actually act as a base, but it doesn't come apart. It doesn't produce hydroxide ions, and it doesn't produce hydronium ions either, not necessarily. It gets a little trickier. That this just has empty orbitals that can donate it. The best way to look at that type of interaction is to use a base that we're familiar with, which is ammonia. And so if you take something like borane, which is BH3, it has, you know from the Lewis structure exercises that boron can be happy with 6 electrons, but it still could use 2 more, right? So it has an empty p orbital that can accept electron density. So this will donate electron density into an empty orbital. So that makes that a Lewis acid, and this a Lewis base. And when it's all said and done, see, this arrow indicates that this is a covalent donor bond. And so once you draw it all out, you just end up with a structure like that, and you have formal charges of minus and plus, but you can no longer really see that both of those electrons from this covalent bond come from nitrogen, but that by definition makes it a Lewis base, and the electron acceptor, a Lewis acid. Okay, here's just a nice illustration for the Arrhenius definition: hydrochloric acid, hydrogen chloride, which is actually gas. Okay, so HCl is actually gas, and when you bubble that, when you pressurize it, just like carbon dioxide, when you pressurize water, you get carbonic acid, and you have the carbonated drinks this way. This is how hydrochloric acid is produced. You pressurize it, and so then all of the hydrogen and chloride breaks apart into chloride and hydrogen ions. So that's why it makes this a strong acid. Now, unlike carbon dioxide, which has an equilibrium, this does not have an equilibrium. So once you pressurize it, it stays in solution, and so that's when we call this aqueous hydrochloric acid. And we have these solutions 6 molar, 12 molar, and like that. So this shows that you have free ions, and the same is true for sodium hydroxide. That's a strong base, no equilibrium. Everything, you can have white pellets of pure sodium hydroxide, and they will dissolve. It's a very exothermic reaction too. If you dissolve sodium hydroxide in water, it's going to get pretty hot. And again, so we have hydroxide ions in solution. The Bronsted-Lowry definition, as I said, is the one that we're going to focus on, and so we're going to look at acetic acid as an example. And it would, when it reacts with water, as an example, this would be the acid. It is donating the proton, and this would be the base, since it accepts the proton from the acid. So this is a weak acid, so we have an equilibrium. We're going to produce an acetate ion. And the base actually has an extra proton now, right? It becomes the hydronium ion. So the original base here, the water, has an extra hydrogen ion or proton, so it actually becomes an acid. It becomes the so-called conjugate acid. And I'm just going to call that the Ca from here on out, and then this is going to be the conjugate base because it has now a lone pair that can accept the proton. So it becomes the conjugate base. And it, as the conjugate base, as an example, can react with water to form acetic acid and hydroxide ion. So here we have a base and an acid, and this becomes the conjugate acid, and this becomes the conjugate base, the hydroxide ion. And you also want to start thinking about equilibrium here, right? So if this is a weak acid, our equilibrium constant is going to be very small. So we're not going to produce a lot of acetate here. But if we have a source of acetate, and that equilibrium is going to go very far to the right in this case because it's going to form more acidic acid. So also, if we had a salt of acetate, like sodium acetate, right? If we took some solid and we dissolved it in water, we would get this exact reaction, right? So a solution of sodium acetate is going to be a basic solution because the acetate will act as a base and produce hydroxide ion. So that's another thing that you might want to keep in mind, that salts can be acids or bases depending on what ions they contain. Something like sodium chloride wouldn't be, okay? Although we still have a conjugate acid-base pair the same way we do for acetic acid. We still have hydrochloric acid as an acid and water as a base, but there's no equilibrium here, forming hydronium ion, which is the conjugate acid, and chloride ions, which is the conjugate base. But it's not really basic. So sodium chloride the chloride will not, again, this is an equilibrium deal here, right? So if we have 100% of the products formed, then the chloride will not react with water to form to act as a base, to form hydroxide. But we still can label these as conjugate acid-base pairs. This is just a more generic conjugate acid-base illustration. I think it works pretty well here in blue. You're showing the proton that's being transferred to the base. And just to emphasize what I've said already, the base becomes the conjugate acid because it now has that extra proton, and the acid becomes the conjugate base because it has a lone pair, right? And so if you look at the structure of acetate, you do have lone pairs here everywhere, but specifically what it's referring to is when this hydrogen bond is broken, an H plus is abstracted, and so that puts a lone pair, that puts these two bonded electrons back onto that oxygen. That's what's indicated here by these two dots on the A minus, and that makes this entire thing A represents the A, and so then A minus can react or act as a base and do that same thing. The conjugate base reacts with an acid in the same fashion. So this is just to reinforce what I've said already. If we look at ammonia is a base and it accepts a proton. It has an extra proton, so this is the conjugate. This is the base conjugate acid pair, right? And if water acts in this particular reaction acts as the acid, it will donate the proton to the ammonia and turn into the conjugate base. It's actually a pretty simple concept. So this is just the summary here, and color-coded. Ammonia turns into ammonium, becomes the conjugate acid. It's pretty straightforward by definition. So the base accepts the proton, becomes the conjugate acid. Let's practice that, right? So in each of these reactions, identify the Bronsted-Lowry acid, the Bronsted-Lowry base, and the conjugate acid and the conjugate base. So this is sulfuric acid. The name itself gives it away, but we can see that just the negative charge here indicates that a proton was probably lost here, or a charge was lost. So the H plus was transferred here to the water. So in this case, and water can be an acid or a base, right? So in this case, this is the acid here. This is the base. And the acid turns into the conjugate base, and the base turns into the conjugate acid. And so this is a strong acid, so we don't have an equilibrium. So this conjugate base will not be a strong one. It'll be extremely weak, if any. But the hydrogen carbonate is, in this case, the hydrogen carbonate is what accepts the proton here. And so this is going to be the base, and this is the acid, which makes this the conjugate acid, and this the conjugate base. It's actually pretty simple. When we come back, we're going to look at equilibrium, the equilibrium constants and how we can work this to our advantage.